Okay, hello and welcome back everybody. So this section is going to be called bases, which is plural of basis, so that's the Greek plural, by the way. Bases, I suppose you could say, if you don't really be Greek about it. So plural of basis and vector representations. Where I want to start is really on this notion of all vector spaces are created out of a fundamental, non-unique, but fundamental collection of vectors. Right, so kind of the classic example we were seeing was when I would write a vector space like C1 V1 plus C2 V2 plus dot 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 plus Cn Vn, such that each of the C's were in C, or maybe R, and the vectors were vectors. So there was always kind of this set of vectors that somehow birthed the vector space, right? In reality, we also came up with this notion of the span, right? It's the span of this collection, Vk, k going from 1 to n. So like there's this fundamental set of vectors that is creating every vector space. Now that doesn't have to be unique, not necessarily unique. Since there are cases where you could have, say, Vk, k equals 1 to n equals, maybe there's a new span of a new collection of vectors, call them Wk, right, where we're not dealing with the same vectors, but maybe their spans are equivalent because one of them is created from linear combinations of the other and vice versa. But the vector space itself is kind of endowed with some sort of natural collection of vectors which creates it. And that's really what the basis is. So I'll define the basis now. A basis for a vector space is a linearly independent, maybe I'll write that out explicitly so everybody remembers what that is, linearly independent set of vectors for which V, the vector space, equals the span. Okay, and I haven't written V or the set there, so I will do that now. Okay, so there I've added in that the vector space is V and then the set is the basis, okay? But what's special here is that we do need this. This is a requirement that they are linearly independent. And what do I mean by linearly independent set? I mean that each V, let's call it V sub I, in this set. So for everything I can pull from the set is linearly independent from the set when I don't consider I in there. Okay, so I'm going to eliminate, we're going to remove I from the set, the indexing set. And if I remove it from the indexing set, then this one needs to be linearly independent of the rest. So I can provide quite a few examples of these bases. So quite a few examples would be something like the set 1, 1, 1, negative 1 is a basis for R2. Since the span of 1, 1, 1, negative 1 equals R2. Now, I haven't proven that to you yet, but I maybe will in the worked examples section. So the span is equal to R2, and this is very important, that 1, 1 is linearly independent of 1, negative 1. So you need both properties to be true. This needs to be true, and this needs to be true. Both must be true for a basis. Now there is a word, if you only have the first case, that the span is equal to the space, that's called a frame. So there's an entire subfield of math called frame theory, where people do work on these sorts of sets where you don't require linear independence. But in the event that you do require linear independence, we call this a basis. And we're going to be using the word basis over and over and over again this semester. Let's look at an example of something which isn't a basis. If I do x squared and x plus 1 is not a basis for this set of quadratic polynomials. Since, well, we can prove that the span of this set is not the whole space fairly easily, which we can see from noting that the regular constant 1 is not in the span. So the regular constant 1 is certainly a polynomial of up to second degree. But we can never recover that out of the span because the span's only giving me the ability to do ax squared plus bx plus b. So the fact that that number and that number are the same, but in the polynomial space they're different, you're never going to be able to just recover 1 because you would need this to be 1, but the moment that b is 1, this b is 1, and so you automatically have x. Must get x for free, but we don't want it because it's a 0x plus 1 over there. So that's an example of something that's not a basis. Now, the moment we have a basis, we have something called the vector representation with respect to the basis. Okay, so given a basis, you can extract a vector representation. And these are incredibly useful because they give us the ability to consider all vector spaces like c to the n, which was, these of like c1, c2, ... cn. I should say all finite dimensional vector spaces. So all finite dimensional vector spaces like c to the n. So that means, in some sense, once we have a notion of vector representations, and we'll see how to do this soon, once we have this notion, these are the only objects we need to study. In finite dimension. So once we know what these vector representations are, all we will have to do is study these sorts of column vectors in the complex numbers. So let's do it. Let's construct a vector representation. See how it's defined. So I'll say definition. Given a vector space V and associated basis Vk, k equals 1 to n, the vector representation of any vector, and I'll use w inside of this space. So I have some other vector w inside of my space, gains a representation. So the vector representation is given by the column vector in c to the n. So it's a column vector c1, c2, ... cn, which is a member of this space, with subscript vk, a basis. So then I write the subscript in here, vk, where these c's have a very specific meaning. The original vector I cared about, w, which is the one I'm representing, you can say w is equal to, the original one I'm representing has to be equal to c k v k. And let's recall from Einstein, that's equivalent to this. K goes from 1 to n, c k v k, which is equivalent to c1 v1 plus c2 v2 plus dot 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 plus cn vn. So in other words, I take w, I take the linear combination of the basis elements that gives me w, and I extract those coefficients. I extract all of the coefficients, and I place them into a column vector. Place the coefficients of basis elements into column vector. So that's what a vector representation is. You place the coefficients of the basis, which gives you any vector, into a column vector. This is going to make a lot more sense when we see a few examples. I think my favorite example probably is this case with the polynomials again. Consider the polynomial, or the quadratic polynomial, 3x squared minus 2x minus 2, and the basis, x squared, x and 1, for the vector space P2, which is defined as the span of x squared, x and 1. The vector representation of 3x squared minus 2x minus 2 is given by the column vector -2, -2, 3. Where I've taken that -2 and put it there, that -2 and put it there, and that 3 and put it there. Now these gain a subscript. I should probably reorder actually the way that I've ordered these. I should reorder this as a 1, an x, and an x squared, a 1, an x, and an x squared. It gains the subscript 1x, x squared, where the subscript is the basis. So this is the basis that I started with. And the reason I was able to write it like that was that this, and this are the three basis entries. So the elements inside of here are the coefficients of the basis elements. I just extracted the coefficients of the basis elements to give myself a vector representation. Now, because bases aren't unique, vector representations aren't unique, and let's look at an example of that. So we'll look at an example where we'll do the same thing. So we're going to consider the quadratic polynomial 3x squared minus 2x minus 2, but we're going to modify our basis. And the basis will now be x squared plus 1, negative 2x minus 1, and x. So we've modified the basis for the vector space P2. So it's the same vector space as before, but we've modified our basis. We're going to gain a new vector representation. So the vector representation of 3x squared minus 2x minus 2 is given by the column vector. Well, I don't actually know immediately in this case. It's going to be the column vector. I'll write it as A, B, and C with the subscript given by my basis elements. What were my basis elements? X squared plus 1, negative 2x minus 1, and x. But we should figure out what these are. To figure out what those are, what I need to do is set up what this is representing. This represents an A, the A multiplying the first term. So I've got A, x squared plus 1. I've got a B multiplying the second term in the basis, 2x minus 1. And I've got a C multiplying the third term in the basis, plus C times x. And I want this to be equal to 3x minus squared minus 2x minus 2. So what I need to do is, as I did in the previous video, expand this to give me ax squared plus a plus negative 2bx minus b plus cx. And if I combine all of my like terms, I have ax squared plus c minus 2bx plus a minus b. So now I'm going to compare the 3 here with a there. I'm going to compare the negative 2 there with c minus 2b there, and compare negative 2 there with a minus b there. So that gives me a system of 3 equations. 3 equals a, negative 2 equals c minus 2b, and negative 2 equals a minus b, which sends me to a equals 3. Not really a surprise there. If I would replace this a with a 3 and then bring it to the left-hand side, I have negative b is negative 5, or b equals 5. And then now I know that b equals 5. If I put b equals 5 there, I have c minus 10, or I add 10 to both sides and recover that c equals 8. So solving that system gives me a, b, and c, which gives me the ability to modify a, b, and c into 3, 5, and 8. So I have a new vector representation. Instead of having this one from before, negative 2, negative 2, 3, I now have 3, 5, 8. So the vector representations have changed greatly just because I changed my basis. But they're both perfectly valid. I'm just working under a different basis, which is why it's pretty important that I include the basis as a subscript so that everybody knows the basis I'm working under. Let's run one more example of this vector representation just in the complex numbers. And we'll do it with respect to 2 different bases so that we can see even how vector representations would change within the complex numbers themselves. So for example, 1, 0, 0, 1 is a basis. And in fact, this very pretty basis is given a special name. It's called the canonical basis. For C2. So that's the canonical basis for C2. We've got another one here. I can do I1, negative I1 is also a basis for C2. Let's construct the vector representation of, well, now this is a little bit interesting. What does it mean when I write 3, 5 plus I down? If I write 3, 5 plus I, which is an element of C2, what is its vector representation with respect to the canonical basis, 1, 0, 0, 1, and the non-canonical one, or one of the non-canonical ones, I1, negative I1. So what changes between the two? Well, it's kind of interesting that I start with a column vector, and then I'm asked to transform it into a column vector to do this vector representation. Let's just see what happens when we do the first case. So 3, 5 plus I should be equal to A times 1, 0 plus B times 0, 1. Well, if I combine all these terms, right, I can distribute the A to both terms there and the B to both terms there. What I find out is I have the vector A over B, and that immediately tells me that 3 should be A, 5 plus I should be B. And so my vector representation against the canonical basis is A is 3 and B is 5 plus I. So I write my subscript here, 1, 0, 0, 1. We see that the canonical basis is the natural basis for elements of C2, and in fact elements of any of the dimensional spaces. And so a lot of times we do just omit that subscript. You can omit it, and that's really what we mean when we write any element of C2 down, unless we specify a subscript. So this is kind of a very common thing that occurs, is the canonical basis is always sitting around, but we should give ourselves the ability to work with some of these other bases, because it doesn't seem like it right away, but once we get deep into the semester, we're going to find out that some other bases are actually quite useful. They can make our lives a little bit easier for specific problems. So let's go ahead and find the basis representation without the canonical. So this is canonical. But let's do this case of the non-canonical basis. So with the non-canonical basis, we're going to end up with 3 and 5 plus I should be equal to A times the non-canonical, which is I1, plus B times negative I1. And if I combine the A's and the B's there, I end up with A plus B, and I end up with A minus B in the earlier case, and A plus B in the second entry. So if I read across horizontally, I find a system of equations. My system of equations is that 3 is equal to I, a minus b, and 5 plus I is equal to a plus b. In the first situation, what does it mean to divide by I? Well, you could divide by I, both sides. This is me trying to solve for either A or B. You can divide by I, but I should just make a remark because it's going to be useful to us the entire semester. Dividing by I is the same as multiplying by negative I. You're going to see me do that shortcut all the time. Why is this true? Well, if you take I times negative I, you get negative I squared, which is negative 1, which is 1. And so it's to our advantage here to just multiply both sides by negative I. And we end up with negative 3I is equal to a minus b. And at this point, substitution method makes a lot more sense. So if I want to do a substitution, I can solve the top one for b. And solving the top one for b gives me that b is equal to a plus 3I. And if I plug that in for b in the bottom case, I get that 5 plus I equals a plus 3I, which is equivalent to saying that if I move the 3I to the left, 5 minus 2I equals 2a. Or if I divide by 2, I can distribute that to both the real and imaginary part. I recover that a is 5/2 minus I. So I found a. And then if I utilize this along with a, I can find b to give me b is 5/2 minus I plus 3I. And I recover 5/2 plus 2I for b. So now I've found a and b. That gives me my vector representation, right? So my vector representation is the vector a over b. So the vector representation in this new space is a, which is 5/2 minus I, and b, which is 5/2 plus 2I. And this is with respect to my modified basis, I1, negative I1. And so there's the vector representation with respect to a new basis, and it's not quite as pretty as the original one, but like I said, we're going to see in the future that it's quite useful to be able to transfer between the two of them. Anyway, that's all I've got for you today. We'll get some more practice later. Bye.